Hello people, welcome back. So if you made it this far in the semester, you ought to be congratulated because we're directly at the halfway point of our studies. And what we're going to do in this chapter is essentially bring a lot of our concepts together to understand direct current circuits. Now there's also alternative current circuits, but in this chapter, the focus will be on direct current circuits. So let's go ahead and focus on that topic. So we have seen that there are things like batteries, resistors, capacitors, and they can all be combined in various combinations. And what we're going to essentially do in the first unit of this chapter, and it's a rather long chapter, is basically teach ourselves how to combine resistors in series and in parallel. So it so comes about that we can combine resistors in series and parallel using rules that are quite analogous to the rules that we learned for capacitors. And in many situations, we might actually find that those rules will serve us well in analyzing the circuit. Now, analyzing a circuit means basically being able to predict the current flow across each and every resistor, the voltage across each and every resistor. If there are capacitors in the circuit, you have to be able to predict the amount of charge on the capacitor and the voltage across each capacitor, and so on and so forth. Now, it turns out that for simple circuits, this idea of combining resistors in series and parallel and combining capacitors in series and parallel allows us to kind of uh, uh, provide the whole deal, namely go ahead and solve the whole problem. For more complicated situations, we have to extend our knowledge. So we have to actually learn about Kirchhoff's rules. And Kirchhoff's rules are basically based on two fundamental ideas. They're based on one fundamental idea which says that the energy of a charged particle that goes through a circuit is actually conserved as it goes ahead and makes a loop in the circuit. So it's based on conservation of energy, and as we know in physics, conservation of energy is a very important idea. The other version of Kirchhoff's rules relies on conservation of charge. So it basically says that the charge coming into a junction is actually equal to the charge going out of a junction. Okay? So in this chapter, we're going to study circuits that involve direct current, the circuitry that is associated with things that are connected to the outlets in your homes and offices is basically based on alternating current, which will of course be part of another later study, but not this chapter. We're also going to learn how to combine resistors and capacitors in various interesting combinations. So let's go ahead and proceed with our studies by basically going ahead and studying resistors in series and parallel. What we're going to do is first understand what happens when resistors are connected in series. So that's shown by this diagram down below on at the right bottom, and we see that if you have a battery with a voltage delta V connected to this circuit, then the same amount of voltage difference will exist between points A and point C. Okay? However, we realize that the same current will have to necessarily flow through the resistor R1 as through the resistor R2. So we realize one important fact about resistors that are connected in series, that being connected in series basically means that if current flows through the first resistor, the same current absolutely has to flow through the second resistor. So that's what we mean by connected in series, namely they're connected end to end. Okay? So with that idea, we say that for resistors that are connected in series, the current flowing through both the resistors is the same. Okay? However, we also say that the voltage difference between points A and C is equal to the voltage between point A and B through the resistor R1 plus the voltage difference between point B and C through the resistor R2. So the potential difference between the resistors is actually divided amongst the resistors, and the sum of the potential differences across each of the resistors adds up to the total potential difference across the combination of resistors. So with these pieces of stage setting, let's go ahead and try to be a little more mathematical. So we see that current I1 across resistor R1 is equal to current I2 across resistor R2, which is actually equal to the full current I flowing through the circuit. Now we realize that resistance is defined as voltage divided by current. And so we can actually go ahead and say that the current I1 is equal to, or I'm sorry, let's go ahead and back up a little bit. So we can actually focus on the voltage, and we can say that the voltage delta V1 is actually equal to R1 times the current I. The voltage delta V2 across the resistor R2 is actually equal to R2 times the current I. And therefore, we can say that the total voltage delta V is actually equal to delta V1 plus delta V2, which is equal to R1I plus R2I, which in turn can be written as R1 plus R2 times I. Therefore, we say that the equivalent resistance Req is just equal to the delta V, that is the voltage from points A to C, divided by the current flow, and we have a perfect relationship giving us delta V in terms of the current I. So we actually go ahead and say that the equivalent resistance is just equal to R1 plus R2 in this situation. Now we can actually go ahead and extend this concept by saying that if we have a whole slew of resistors connected in series, then the total resistance of that configuration is just equal to the arithmetic sum of the multiple resistors that are connected in series. So the equivalent resistance of a series combination of resistors is always larger than the algebraic sum of the individual resistances. And so if you connect resistors in series, then you'll always get a effective resistance or an equivalent resistance that is greater than each individual resistor that is going into that series combination. Now this all makes sense because you think of resistance as the ability of an individual resistor or a combination of resistors to actually resist the free flow of electricity. And if you combine two resistors end to end, what you're effectively doing is that any electron that wants to go through the circuit now has to go through the first resistor and experience some amount of resistance to its free flow, and go through the second resistor sequentially and also experience some amount of resistance to its free flow. So it's only natural that the resistance should increase. Now, despite your willingness to connect uh, devices in series, there's actually one practical deficiency associated with connecting things in series, which is that if one device in the circuit conks out, it basically creates an open circuit, and all the devices in that circuit then become inoperative. So in practical situations, for example, in your household, you will not have a situation where devices are connected in series one to the other, or it's actually not a very beneficial configuration in which to combine devices. But if you're dealing with a situation where you have a particular resistor and another particular resistor, and you want a resistor that is larger than each of those individual resistors, then indeed you can put together the thing in series and get some advantage. So these are just showing you three different equivalent ways of thinking about resistors. Notice that a light bulb is actually a de facto resistor because it provides a resistance to the free flow of electricity. That is the only way in which the light bulb actually generates a lot of heat and also a lot of light. Now, for an incandescent light bulb, the reality is that it generates more heat than light, but the light is the only useful part of what you get from an incandescent light bulb. That is less so for an LED light bulb, which is why LED light bulbs are more power efficient. So with this understanding, we can actually go ahead and develop a good appreciation of resistors in series. Now let's go ahead and move on to resistors in parallel. So in series, the current only flows through one single path. In parallel, what happens is that there are multiple paths through which the current can flow. So that is the fundamental difference between series and parallel. And now let's go ahead and transition over to the process of connecting resistors in parallel. So in parallel, what happens is that between the points A and B, we realize that both those points are connected to the ends of the battery, and so we should expect there to be the same voltage drop between points A and B if we traverse through resistor R1 as we should expect if we traverse through resistor R2. So therefore, we can actually say that resistors that are connected in parallel will indeed have the same potential difference across each of the resistors in that combination. And so we can actually go ahead and say that it is in fact the current that splits. So the current I that comes through the junction A out here is actually split into a current I1 that goes through the first resistor R1 and a current I2 that goes across the second resistor R2. We can therefore say that the total current I is actually equal to I1 plus I2. And for each of the I1 and I2, we have a simple expression. We realize that I, from the fundamental notion of resistance, is equal to voltage divided by current. We realize that I1 should just be equal to delta V divided by R1, and I2 should be equal to delta V divided by R2. So this allows us to write this expression as delta V times 1 over R1 plus 1 over R2. Let's go ahead and massage this equation just a little bit. So we can write I divided by delta V is actually equal to 1 over R1 plus 1 over R2. Notice delta V is the same across the two resistors. However, I'm sorry, not capacitors, but resistors. Delta V is the same across the two resistors. However, the total voltage, the total current is in fact the sum of the currents, and so we can actually say that the total current divided by the total voltage should actually be equal to the reciprocal of the equivalent resistance. So we say that 1 over Req is equal to 1 over R1 plus 1 over R2, and that gives us the essential idea that resistors combined in parallel are indeed to be added reciprocally. Okay? With this understanding, we go to the next transparency, which actually shows equivalent depictions of resistors that are connected in parallel. And then we can actually go ahead and realize that because of this reciprocal addition, the equivalent resistance of a sequence of resistors that are connected in parallel is always less than each of the individual resistances. And this can be understood individually by realizing that a single electron that is trying to go through a circuit which has resistors that are connected in parallel always has the option of going through one of the resistances or the other resistance. It's just like saying that if you have a multi-lane highway, then traffic can move much faster on a multi-lane highway than it can move on a single lane highway. You must have seen this when the lanes of a highway get constricted due to some repair work. Then of course all the traffic that is going on a two-lane highway will then be diverted along a single lane, and you will see that the traffic moves faster in the part of the highway that has two lanes than the traffic that is moving through that segment of the highway that has been restricted to having only a single lane. So with this intuitive understanding of what happens, or with this intuitive analogy to a single lane and a multi-lane highway, we can actually appreciate that the resistance in a set of resistors that are connected in parallel will in fact be less than the two individual resistors that go into making that parallel connection. So with that understanding, let's move forward and understand that in reality, household circuits are always wired so that they're connected in parallel. The reason for that is very simple. The reason for that is that when household circuits are connected in parallel, or when multiple devices are connected in parallel, the voltage across each of those devices remains the same. And you must have noticed that all the devices that you deal with are all rated at 110 volts, because 110 volts is what is the amount of voltage that is promised to be supplied out of the outlet in your homes or in the office. And the significant advantage of that is that if one of the devices conks off, that doesn't affect the other devices, because the remaining devices will still see the same voltage difference, and they will still be able to keep functioning because current will be flowing through them. So this is the reason why household circuitry is always connected in parallel, never in series. So with that, let's go ahead and do a simple thought question. So I'll go ahead and do thought question number 1 together with you all, and then we'll do thought question number 2 you all will do thought question number 2 by yourselves, and will of course practice both of them in class. So with that, let's go ahead and think about this situation. There are two identical resistors. Initially, they're connected in series, and they're connected in series across a certain idealized battery. Ideal battery but necessarily means that the internal resistance of the battery can be effectively considered to be zero. So when we have such a situation, then the amount of power drawn is 20 watts. What does that mean? If we take each of the resistors to be R, then we realize that connecting them in series will give us a resistance of 2R. So we say that the 20 watts is actually equal to the power delivered in the initial configuration. Okay, now realize that we have multiple definitions of the power consumed in a resistor, so we can actually write the power consumed in a resistor as being equal to I, the current flow, times the voltage, but it can also be written as Ri squared. It can also be written as V squared over R. Now, which one you use in a particular circumstance uh, depends entirely on convenience and what the problem is all about. So we realize that all these three definitions of the power consumed by a resistor are completely equivalent, completely interchangeable, yet in one circumstance one might be more beneficial than the other. So now in this situation, we realize that the battery always supplies the same voltage. So we can actually say that the voltage is the same, therefore V squared over R is the appropriate thing to use. And in the first situation, we have a situation where let the battery supply a voltage V, then the power consumption will just be equal to V squared divided by the equivalent resistance for the series configuration that we have found, which is 2 times the resistance of each individual resistor. In the final configuration, we're told that we break that series circuit apart and instead connect the two resistors in parallel. What does connecting the two resistors in parallel mean? It means that the equivalent resistance has to be obtained by a reciprocal addition. So we have 1 over Req is equal to 1 over R plus 1 over R for each of the two identical resistors. So 1 over R plus 1 over R is just 2 over R, but realize that that's not the answer. We have to flip the numerator and denominator. So the equivalent resistance is just R over 2 in the parallel situation. And so we're going to go ahead and say that in the final situation, the power consumption is actually equal to V squared divided by R over 2. Now notice that this tells me that the denominator in the final configuration is 1/4 the denominator in the initial configuration, which means that the power is actually 4 times larger in the final configuration than in the initial configuration. If you want me to write this out more explicitly, I can write this as 4 times V squared over 2R. Okay, that's just a matter of using fractions appropriately and relating it. So I obtained that the result that the power in the final configuration is equal to 4 times the power in the initial configuration, which is why we identify E as the right answer for this problem. So with this understanding, let's go ahead and move on. You guys should take a little time off and mull over thought question number 2, maybe try to prepare an answer for it. And so with this understanding, let's basically go ahead and move forward. So we now understand that the overarching game plan for combining configurations of resistors in series and parallel, like the one shown in figure A above, is quite analogous to what we learned about capacitors. So we realize that the 8 ohm resistor and the 4 ohm resistor are in series together out here. And so we can actually say that they add arithmetically to basically give us the 12 ohm resistor out here. The 6 ohm resistor and the 3 ohm resistor are in parallel, so they add as 1 over 6 plus 1 over 3. This actually becomes 1 over 6 plus 2 over 6, which is actually 3 over 6, which is just equal to 1 over 2. Now notice that this is the reciprocal of the equivalent resistance, and so we realize that these two resistors, the 6 ohm and the 3 ohm resistor that are connected in parallel, is equivalent to the reciprocal of 1 over 2, which is just 2 ohms. Now, the next step is to actually go ahead and evaluate what happens when we have a 12 ohm resistor and a 2 ohm resistor, and we actually see that that is equivalent to having a 2 plus 12, which is just a 14 ohm resistor. Then the next part of the problem, so we see that we have to always go ahead and work our way through going from the more complex configuration to the less complex configuration, sequentially using our rules for series and parallel combinations of resistors. Now, the next part of the problem, we're told that we have a voltage of 24 volts connected across the ends A and C. That is same as connecting a 24-volt battery in figure A from the terminal A to the terminal C. Okay? We're asked to find, or we're asked to solve the problem, which basically is equivalent to saying that we are asked to find the voltages across each of the resistors and the currents across going through each of the resistors. So let's go ahead and see how that goes in the subsequent picture. So in the subsequent picture, we see all the voltages and all the currents. I'm sorry, in this picture, we've essentially solved the problem. Namely, we found the equivalent resistance between points A and C to be 14 ohms. We're now going ahead and putting a voltage of 24 volts across points A and C in each of these three figures. So what we do when we want to solve this part of the problem is that we work backwards. Namely, we've gotten an equivalent resistance, we then move our way backwards back to the original figure that we had to deal with. So if we have 24 volts across a 14 ohm resistor, then the amount of current I is just equal to 28 volts divided by 14 ohms, and that is actually equal to 2 amps. So we realize that we have 2 amps flowing through the circuit shown in figure C. Therefore, we should have the same 2 amps flowing through the circuit shown in figure B. Now, in figure B, if we have 2 amps flowing through the 12 ohm resistor, then we realize that between points A and C, we should have a voltage difference given by 12 ohms times 2 amperes, which is actually equal to 24 volts. Okay, so across points A and B, we have 24 volts in this circuit. Now, between points A and C, we have 28 volts. I'm sorry, I originally put 20, I should have put 28 across the points A and C. Okay, so sorry for that misconception. It's actually given out here, and I hope you picked up from there. So we actually have 28 volts divided by 14 ohms through points A and C in this part C out here. Therefore, we have 2 amps flowing through this point and this point in part B out here. And if that is the case, we can actually go ahead and have 24 volts going through points A and B. We have 28 volts across points A and C, and therefore between points B and C we have 28 volts minus 24 volts, which is actually equal to 4 volts between points B and C. Okay, so to bring it back, we have 24 volts between this point and this point. Okay, and we have another 4 volts between points B and C. So we have 4 volts across here. Now, if we have 4 volts across points B and C, we can actually say that the amount of current flow across resistor, the 3 ohm resistor, is just given by I, which is equal to 4 volts divided by 3 ohms, and so the current in this part of the circuit is just given by 4 over 3 amps. The current flowing through the 6 ohm resistor is just given by 4 volts divided by 6 ohms, which is actually equal to 4 over 6. And we now realize that 4 over 6 plus 4 over 3 adds up to 2 amps, which is the original current that we had flowing through the entire circuit in figure B. So we still have 2 amps of current flowing through the 8 ohm resistor and the 4 ohm resistor, and we can therefore say that between the 8 ohm resistor we have a voltage drop of 8 times 2, which is 16 volts, and we should have a total of 24 volts between points A and C, and so between the 4 ohm resistor we have a voltage drop of 24 minus 16, which is actually 8 volts. So out here across the 4 ohm resistor we have a drop of 8 volts. Across the 8 ohm resistor we have a drop of 16 volts, adding up to a total drop of 24 volts across here and here, and we have another drop of 4 volts between the 3 ohm and the 6 ohm resistor. They both have the same voltage drop also realize that we have 2 amps flowing through the 8 ohm resistor and the 4 ohm resistor, and that 2 amps of current splits into 4/6 amps of current flowing through the 6 ohm resistor and 4/3 amps of current flowing through the 3 ohm resistor. Also notice that 4/6 plus 4/3 adds up to 8 plus 4/6, which is actually equal to 12/6, which is 2 amps. So we actually see that everything is ship-shape with respect to this particular circuit. So with that understanding, let's go ahead and move on to the next problem that we have out here. Again, it is solved in the same style that we've developed for understanding how to solve capacitor problems. Namely, we go ahead and simplify the problem, moving from left to right, moving from one equivalent circuit to the other, and then we go ahead and move backwards from right to left if we're asked to find the voltages and currents in each of the resistors. So let's go ahead and first realize that we can combine the 4 ohm resistor and the 12 ohm resistor, and we have to do so reciprocally. So we realize that 1/4 ohms plus 1/12 ohms is just equal to 3/12 plus 1/12, which is actually equal to 4/12 ohms. And we have to take the reciprocal of that, which is actually equivalent to saying that we have 3 ohms in here. So we go from the left panel to the middle panel where the resistance RA is 3 ohms. Okay? Now that we have that figured out, let's go ahead and do the next step, which is to realize that the 5 ohm resistor and the 3 ohm resistor are in series in the middle panel. So they should actually combine together to give 5 plus 3, which is actually equal to 8 ohms in the circuit on the right panel. Now in the next problem, we're told that we have 24 volts between points A and B. So across these 2 points, we have 24 volts. And we're asked to go ahead and solve this problem. Notice, of course, that we can combine the 24 ohm resistor and the 8 ohm resistor because they're in parallel, and we can find an equivalent resistance. So we can actually go ahead and say that the total equivalent resistance is actually equal to 1/24 plus 1/8, which is actually equal to 1/24 plus 3/24, which is actually equal to 4/24, which is same as 1/6. So if this is 1/Req for the entire circuit, we say that the 24 ohm resistor and the 8 ohm resistor connected in parallel is just equivalent to an equivalent resistance of 6 ohms. So this entire configuration on the right behaves like a single resistor with a resistance of 6 ohms, and now we're told that we have 24 volts connected across the ends of this situation, which is equivalent to saying that we have 24 volts connected across the ends of the figure on the left. Okay, so let's go ahead and systematically work our way from right to left now. In this figure, all the resistances are solved. Now let's go ahead and work our way through. So we understand that the current in this leg of the circuit is just equal to 24 volts divided by 8 ohms, which is actually equal to 3 amps. The current in this leg of the circuit across the 24 ohm resistor is just given by 24 volts divided by 24 ohms, which is actually equal to 1 amp. So there's a total current of 1 amp plus 3 amps flowing through this entire circuit. So this current out here is 4 amps. Okay? Now realize that the same situation prevails out here. So you have essentially 3 amps flowing through this bottom leg of the circuit in the middle panel, and you have 1 amp of current flowing through the top leg of the circuit in the middle panel. Therefore, we realize that across the 5 ohm resistor, we have 3 times 5, which is actually 15 volts across this part. But of course, we know that between points A and C, we have 24 volts. That tells us that between the 3 ohm resistor, we actually have 24 volts minus 15 volts, which is actually equal to 9 volts. So there's 9 volts across this 3 ohm resistor, and that gives us the solution of all the resistors in the middle panel. Now we actually have to go back to the original left panel for which we're actually interested in the answer. So we realize that we still have 3 amps here, and we have 1 amp out here. We don't have to do anything with the current flowing in the 24 ohm resistor because that's already set at 1 amp. We still have the same 3 amps flowing through the 5 ohm resistor, but now realize that between this point and this point, I have 9 volts. Therefore, I can say that the current flowing through the 12 ohm resistor is just given by 9 volts divided by 12 ohms, which is actually equal to 3/4 of an ampere. And the current flowing through the 4 ohm resistor is just given by 9 volts divided by 4 ohms, which is actually equal to 9/4 of an ampere. Realize that 9/4 plus 3/4 adds up to 12/4, and that is just 3 amperes. So the 3 amperes that is going through the 5 ohm resistor is actually splitting into 2 parts, 3/4 of an amp going through the 12 ohm resistor and 9/4 of an amp going through the 4 ohm resistor. So this gives us an entire solution of all the voltages as well as all the currents through each and every resistance or through each and every part of this circuit. Of course, I should actually go ahead and write down 15 volts across the 5 ohm resistor also, just to make the solution complete. And this gives us a complete solution of the circuit on the left, in the left figure, which is in fact the solution of the entire circuit problem. So this tells us how to solve these types of circuit problems. And now let's go ahead and move forward. So what we have next lined up for you is a little bit of a more interesting and challenging problem. Let's go ahead and think about this problem. It tells us that we have a three-way switch S. This switch can remain in the middle, in which case it doesn't connect to either of the two ends, or it can be thrown towards A, in which case you have a parallel connection between R2 and the other resistor R2, or alternatively, it can be thrown downwards so that it connects to point B. Now realize that when it connects to point B, you essentially have a situation where the current that is flowing here would much rather not flow through the resistor R3, but would rather take the path of least resistance, essentially completing the circuit out here. So realize that in the 3 parts of the story told to us in this problem, we have a situation where let's draw out the 3 circuits that arise and analyze them. So in the first part, basically, the switch S is in the middle, which means that this resistor R2 out here is left dangling, so it doesn't participate in the circuit, and you have only one single circuit that goes around the circuit like this. So the resistor R1, R2, and R3 are in parallel, and for the first part of the circuit, we could actually say that for the first part of the circuit, R1 plus R2 plus R3 gives us, I'm sorry, R1 plus R2 plus R3 gives us the effective resistance. Now let's go ahead and erase all different parts of this diagram that we have shown and consider what happens when we have the switch thrown towards A. When the switch is thrown towards A, we realize that this R2 and this R2 come to be in parallel, which means that across these two ends, we have R2 and R2 being in parallel. So the equivalent resistance out here is just equal to R2 divided by 2. So we have R1 and an equivalent resistance of R2 divided by 2 and the resistance R3 all in series. So we say that in the second part of this problem, the effective resistance is R1 plus R2 divided by 2 plus R3. Now let's go ahead and analyze what happens in the third version of this problem. And in the third version of this problem, we have a situation where the switch is thrown downwards. So when the switch is thrown downwards, we have a situation where the current that is coming here does not want to flow through the resistor R3. So the resistor R3 is as good as cut out of the circuit because the current wants to take the path of least resistance and go ahead and flow through the circuit out here. So the current essentially comes here, goes here, goes here, and goes back because it simply does not feel any need to flow through a resistance if there is a path where there's no resistance. It's like saying that if I gave you the option of doing homework or not doing homework, then not doing homework is the path of least resistance, so nobody would do homework, right? So it's exactly similar. So we have a situation where in this situation where the switch is thrown to B, we have R1 plus R2 being the only two resistors in series, and so in the third circumstance we have an equivalent resistance of just R1 plus R2. Okay? So now let's go ahead and solve the actual problem, and that is shown to us all over again in a slightly smaller format in this situation. So what are we told? We're told that with the switch thrown to A, or I'm sorry, we're told that with the switch in the middle, we have a current of 1 amp in this circuit, and the battery itself has 6 volts of voltage. So we say that 1 amp, so this is part 1, 1 amp is equal to the voltage of 6 volts divided by the equivalent resistance that we had in the first situation, which is just R1 plus R2 plus R3. This tells us that R1 plus R2 plus R3 is equal to 6. So R1 plus R2 plus R3 is equal to 6 ohms. In the second situation, we have the switch thrown to A. In that situation, we saw that the two resistors R2 and R2, which are connected in parallel, or we saw that the two resistors are this R2 and this other R2 are connected in parallel, and then we have a situation where they effectively act as a combined resistance of R2 over 2, and so we can actually say that in the second situation, or in the second part, we have a current of 1.2 amperes, and that is equal to 6 volts divided by the resistance R1, which is in series with an equivalent resistance of R2 over 2 plus the resistance R3, which is in series, and that tells us that R1 plus R2 over 2 plus R3 is actually equal to 6 divided by 1.2, which actually turns out to be 5 ohms. In the third part, we're told that the switch is in fact connected to the point B. In that case, the current totally bypasses the resistor R3 and prefers to take the path of least resistance, which is through the switch to the point B, and so only the resistors R1 and R2 are in the circuit and in series. And so we say that in this situation, if the current is told to us to be 2 amperes, then we have 2 amperes is equal to 6 volts divided by R1 plus R2. Okay, so this tells us that R1 plus R2 is actually equal to 6 divided by 2, which is 2 ohms. Now notice that if R1 plus R2 is equal to 2 ohms and R1 plus R2 plus R3 is equal to 6 ohms, then we can immediately combine these two facts to realize that R3 is just equal to 3 ohms. So this tells us that R3 is immediately equal to 3 ohms and R1 plus R2 should together be equal to 6 ohms. So we have a situation where using this fact in the first equation, we can actually get R1 plus R2 is equal to 6 minus 3, which is actually equal to 3 ohms. In the second equation, namely this guy, we realize that R1 plus R2 over 2 plus 3 is equal to 5, which basically means that R1 plus R2 over 2 is actually equal to 5 minus 3, which is 2 ohms. Okay? So this gives us two equations in two unknowns. So we have two equations in two unknowns, and therefore we can solve for them. So it's very easy to obtain the fact that R2 over 2, so if I subtract one from the other, if I subtract the lower one from the upper one, I get R2 over 2 is equal to 1 ohm, which means that I directly get R2 to be equal to 2 ohms. And then that immediately tells me that R1 is equal to 1 ohm. Okay, so we've actually gone ahead and solved the problem. We can see that it all fits because the top equation tells us that R1 plus R2 plus R3 is equal to 6. So 1 plus 2 plus 3 is equal to 6. In the second equation, we're told that R1 plus R2 over 2 plus R3 is equal to 5, which means that 1 plus 2 over 2, which is just 1, plus 3 is equal to 1 plus 1 plus 3, which is equal to 5. That's correct. And then we're told that in the third equation tells us that R1 plus R2 is equal to 2 ohms, which is basically like saying that 1 plus 2 is equal to, no, I'm sorry, the third equation tells us that R1 plus R2 is actually equal to 3 ohms. It's good that we corrected it. And that tells us that, and that actually went ahead and told us that R3 is equal to 3 ohms. So we realize that 1 plus 2, R1 being 1 and R2 being 2, actually adds up to 3 ohms. So sorry, little slip out there. This equation is correct. Just the way I wrote down this equation, this should have been modified to have the number 3 out here. Okay? So with this, we've solved this problem. Of course, all these numbers are correct out here and here and here. So we solved this problem correct, but there was a slight mistake in writing it down. So let's go ahead and move on. And this actually allows us to do a little recap of the entire situation. So in this situation, we're told that we have capacitors and resistors, and we see what happens when they're connected in series and parallel. So we see that capacitors connected in series results in a situation where the total voltage is in fact the addition of the two voltages. And for resistors combined in series, we also have a situation where the resulting voltage is the addition of the individual voltages. The total charge that you can draw from two capacitors in series is the same as the charge in one of them, and therefore they have both the same charge. Now, when dealing with resistors, we're not interested in charge but in current, and we see therefore that they have both the same current. When two resistors are connected in parallel, we realize that both the resistors will have the same voltage across them. I'm sorry, when two capacitors are connected in parallel, we realize that both will have the same voltage across them. Likewise, when two resistors are connected in parallel, we see that the two resistors will also have the same voltage across them. However, when two capacitors are connected in parallel, we see that the total charge that you can draw from that configuration is in fact the addition of the individual charges on each of the two capacitors, and the total current that you can draw from resistors that are connected in parallel is actually the addition of the individual currents across the two resistors. So with that understanding, we realize that the fundamental difference, so all the things that we say about charges for capacitors goes over to being currents for the resistors, because in capacitors we care about the charge on the circuit, or while in resistors we care about the current flowing through the circuit. However, realize that our definitions of capacitor and resistor are a little upside down relative to each other. In other words, the voltage appears in the denominator when defining capacitors. The voltage actually appears in the numerator when defining resistors. And if you think about current flow as just being the motion of charges, then the charge part appears in the numerator when defining capacitors, and the charge per unit time, which is current, appears in the denominator when defining resistors. Therefore, it's simply because of this difference in the definition that we have a situation where capacitors in series sum reciprocally, however, capacitors in parallel sum arithmetically. The situation for resistors is exactly opposite. So, resistors in series sum arithmetically, and resistors in parallel sum reciprocally. So as long as you understand where this difference is coming from, you can just remember one or the other. You can say that resistors in series sum arithmetically and resistors in parallel sum reciprocally. And if you're asked what happens to capacitors, you just flip it. So you basically say that capacitors in series sum reciprocally, whereas capacitors in parallel sum arithmetically. Okay, so with this understanding, we have a full deck of cards, or a full deck of insight with respect to resistors and capacitors connected in series and parallel. And with this, I will basically thank you for your attention and hope to meet you in the next unit. So thank you very much and see you all soon. Thanks a lot. Bye-bye.